is, I don't see any like y values anymore, where I did with the horizontals. But the thing is, you do see y values. This one is y equals this. The blue one is y equals that. And the equation you need to solve right now, let me use a different color. The equation you need to solve right now is that x plus 8 over 3 equals negative 2 times x plus 1. Now, of course, you could solve that manually. You can do all your Lego manipulatives to both of it. But you can also just get from a more holistic point of view. We don't have to solve this manually. We can use the graph. For example, is x equals 3? Is x equals 3 a solution of this equation right here?
No.
Why? Why is it not a solution of that equation? When x equals 3, what does y equal on this blue line? What does y equal on the blue line? Ish. Give me an ish on this one. Looks like about 3.5. Okay? When x equals 3, what does y equal on the green line? Not 3.5. Something negative, yes? Something negative. Therefore, 3 cannot be a solution to the equation, because in order for 3 to be a solution to the equation, whatever number it equals on the blue line, it would also have to equal on the green line, yes? So, let's pick a different, let's pick 0. How about 0? Well, x equals 0. Is that a solution to this equation? When x equals 0 here, what does y equal on the blue line?
2.67.
It's our y-intercept. It's 2.67 from before. How about when it's 0 here, what is it here?
2.
Are they the same? No, they're not the same, they're different. There's only one place where the same x value will make the same y value. And therefore we've solved the equation. And where is that? Where is that, Tammy?
The intersect?
Where they intersect! This is what you learned. You probably have forgotten it by now. But in your last algebra classes, you learned that. Where you find the intersection of two lines, yes, the x values are the same, for sure, which is negative 2. The y values are also the same there. And that's what makes this equation true. If you plug negative 2 into this side, you get the same end result as plugging negative 2 into that side. So negative 2 is the solution to the equation, because that's the one that makes the left-hand side and the right-hand side equal. That's what you're after. That's what you're after. Can you solve it by number crunching, by moving stuff around, by multiplying and by subtracting and by... Yes. But if you're given the gift of a graph, which you're going to have a lot in this class, you're going to have a lot of that in this class, it makes sense to use the graph, please.
How do you know what this question is asking?
Because you have to solve that. Every one of these is solve the equation for x. If you look at the instructions from above, they carries all the way down. All 10 of these are being solved for x.
Okay.
So you need to tell me what x is in this equation to make it true. That's the true part. X has to be negative 2. You've just solved it. Please.
Are you always looking for an intercept if you see an equation like this?
Can
you jump to that assumption?
You can. But most students, we didn't on those first 4. We didn't go straight to a graphical analysis. We solved them manually. My point is, though, very often you're going to want to solve stuff graphically. And this is one of those things you learn like 95 and 65. But yeah, every equation has a graph associated with it.
So you could skip all the math.
You can.
Two equations.
You can. There are entire branches of mathematics that do just that. They go straight to the graph and look for intersections.
Okay.
Yeah, I'm just trying to bridge that gap. I'm not exactly sure who's with me from the beginning, who's with me after 3 examples, 4 examples. It's one of those, like I said, Math 65, Math 95 tools. But depending on who you had in these classes, they may have done less graphic work than just manual work. But yeah, every equation that you've ever solved has a graph like this associated with it. And where they intersect is the solutions you're interested in. Absolutely. Please.
How would you do that mathematically, though, if you're doing it?
If anybody wants to see the mathematical crunch of that, I don't want to focus on that too much in 105 because I don't want to turn the little bit of equation solving we're doing. I know is stressing you guys. I can tell. Stick around after class. I'd be more than happy to walk you through it. I don't want to get too bogged down in too much manipulation of algebraic expressions, because that's not what Math 105 is all about. But happily, stick around for class. We'll walk through. We'll do all these last little few. Please.
Can you actually put those both into the calculator and then go under the thing that says where x equals, right? And it'll just tell you that too.
Yeah, but I've done one better. Because this is what you would do with the TI. If you were to use your TI to do exactly what you're saying, Tim, this is what you would do. You would graph both lines and use the intersect command. That's what you're describing. It's the second calc command, the intersect command.
Yeah.
I've done one better because I can do it in color. Your TI can't. This is what you would be graphing in your TI, and then you'd be second intersecting. Boom, and it would find it right there for you. So in other words, you are doing that right now. It's just you haven't made the connection yet. Well, you have now. This is what your TI, use what you and your TI would do. Exactly. Go ahead, Blake.
How about the number crunching? I mean,
Yes.
Would that make it easier? Let's say we didn't have the graph to work with.
If you didn't have the graph to work with, your choices are make the graph, like Tammy's describing, or crunch the numbers, which I'll be happy to share with you after class. Yeah, I mean, if you're given just that, for starters, without the graph, which again, the point of this course is not to do that. We're going to discover those in context, generally with graphs. Then we have to deal with them. But if you had just that and nothing else, your options are to create the graph like that and work with it, or deal with that on its own terms. If you want to see how, after class, I'm more than happy to sit down with you guys and knock them out. But I don't want this to turn into just another blindly solving equation class. It's just that we will encounter things like this as we go through the class together. I want to make sure we know how to deal with them as we hit it. Let's look at the last couple. And then we'll move into where they're going to show up. Where they're going to show up in context of where they're going to show up. Please, yeah?
So on the next one, does that mean that like you're saying x plus 8 over 3 equals x plus 8 over 3?
Hey, hold tight, hold tight. I think I see, I love asking these questions. I pick things up from you guys. I pick things up. So the first few we did 0 equals negative 2 times the quantity x plus 1. And we thought 0, that's y. Y equals 0. And that equals that. The next one was 0 equals x plus 8 over 3. And you're like, okay, that means y equals 0 again. And then we saw 6 was x plus 8 over 3. And now y was 6. And then we saw this bastion. X plus 8 over 3 equals that. And you're like, oh, they're equal to each other, which means both this y and that y have to be equal to each other. So now there's this new one, which looks partially like the ones over there, but it's got this goofy little x. X equals, right, but that part, x plus 8 over 3 you already recognize, correct? That's the blue bit. That's the blue bit. X plus 8 over 3. That's the new equation we got to look at. So we know what this is. This is this blue line right here. Yes, that's that blue line right here. You see how this x right here? This x is in the same place the 0 was and the 6 was. And what were those again? Those were just y's. Y equals 0, y equals 0, y equals 6. What's y equal to now? Y equals x. Y equals x. What the hell does that mean? What does y equal x mean?
Does that mean that x and y are going to be the same number?
Well, I think that's what it means, yeah?
So you're looking.
So can you give me a point on the graph? Which color should we use first of all for y equals x?
Orange.
Orange? Can you give me a point on the graph where y equals x?
4.
4, 4? 4, 4? Boom. Ba-boom. I think you guys may have just discovered the solution, yes? Can you give, just to see why we might say it's a solution, can you give me another point where y equals x?
2, 2.
2, 2? Can you give me another point where y equals x? Anyone you want! There are infinitely many of them. This is a question Blake had earlier. There are infinitely many points. I'll give you one. How about the origin's one, right? 0, 0? How about some other ones? Actually, we don't need any more. Because haven't we discovered where they all are once you have 2 on the board? You guys ever use a chalk line to make a line on a piece of wood or to the ground? As soon as you have 2 points on a line, you've got them all. All you gotta do is connect them then. This is what the line y equals x would look like, yes? That's what the line y equals x would look like. But you guys, the first point you picked up there, 4, 4, you solve the equation. Because that's where the line y equals x hits the blue line, x plus 8 over 3. So you got the solution. The solution, put it up here, y equals x. The solution is that x equals 4. Because that's where the x-coordinate, where the lines intersect each other. Could you solve it manually? Could you multiply by 3 and start doing all the algebra? Yes, of course you can. But the question is, and thank you for asking it, what is that x? What does that x mean? It means the same thing this means. It's just it's a different line behaving in different ways. It's the same thing you have to do when you're looking at the cost of college over time and the rate of inflation over time. Where are you interested? You're interested in where they meet. Because at where they meet, that's when college exceeds the cost of inflation, which means the rate of growth of the cost of college is more than the rate of growth of the cost of inflation. FYI, it already happened like 25 years ago. I just read an article about it recently. The cost of college increases something like 7% a year on average. The CPI increases about 3% a year on average. No, the article's point was that no longer can a student work a summer job and offset a large chunk of their college bills. They now have to take out loans, which are then repaid poorly when you start working full time. But you see, the point of that story is that's what this is. That's what this is. Rate of growth of the cost of college, rate of inflation. When they hit is the equilibrium point. Past where they hit is why we're having a discussion about the article. You see what I'm getting at, friends? All of that stuff, in order to talk about that intelligently, you have to know how to identify these parts of the graph. All I've done is I stripped the context away for now to focus on the finer points of it. So learning how to use the Phillips versus using the Phillips. That didn't work very well last week, did it? Let's not talk about the Phillips. Fair? Ask me questions about that before I erase, because I want to get the next one on the board too. Tammy?
So when x equals y equals 4, how do you break that?
Oh! What's the variable in this equation? What's the variable? X. So what is x at the intersection?
Oh, okay.
4. That's the solution. The solution is 4. If you guys want to see manual solution, we'll do it after class. Happily. 2 minutes. We'll solve all
I
this.
figured that one out.
Oh, good.
That one I
We'll deal with that one after class, happily. But you don't have to. Every solution, every equation you ever have solved has a graph like this behind it. Every time you read an article about the rising cost of blah, not keeping pace with blah, both of those blahs have graphs that somewhere are intersecting. They are somewhere intersecting. Either they've already happened, they're going to happen, or they're in the process of happening. But all of that is governed by math like this. Every single bit of that is governed by math like this. I know sometimes the inner workings like this kind of like, oh my God, it's like giving me hives like it did back in '65. I totally get that. I totally get that. But you have to understand that in order to talk intelligently about what you then read in the news. Cool?
You don't get tricked by the bison running down the road.
Oh, damn bison. Exactly. Let's do one more. Let's do one more. Let's do one more, and I think you'll have had enough algebra, and we can start applying the algebra to context, which is what I care about in Math 105. I don't want you to think Math 105 is all about just solving equations like this. It's not. It's about making sure when you encounter an equation in context, it doesn't run screaming like the damn bison down Yellowstone's highway. You're like, I'm going to stand in, don't stand in front of bison, just FYI. But I can stand in front of the damn thing and take it head on. Next one, what does it look like? Negative x equals negative 2 times quantity x plus 1. So I recognize part of that, yes? Negative 2 times the quantity x plus 1. What I don't recognize is that negative x. I don't recognize that. Because negative x is in the place y is, yes? Now in the last one, x was in the place y was. And we started making up points right away from that one, didn't we? We started saying, well, does that mean, I think you asked, tell me your name one more time. Was it Brittany? Brittany, you asked, does that mean x equals y? I said, hell yeah. And then you guys started throwing out points. 4, 4, 2, 2, 0, 0. Which was 0, 0. Is 1, 1 on that last equation? 1, 1? Negative 1, negative 1? A half? I mean, all of those. X equals y. What does y equal in this one? the opposite of x. Well, that's kind of clever now. Let's use red. Because what we have to do now is, we know, first of all, you know you can ignore the blue line, yes? This equation has nothing to do with x plus 8 over 3. I can't take it away in my PowerPoint, unfortunately. I apologize. Nor on your little worksheet there. But the blue line is off the table. We're all looking at the green line. So this side of the equation is the green line. This side of the equation, though, we need a new line for that one, yes? We need the line where y equals negative x. Can anybody give me a point that lies on the line y equals negative x? Or, more properly said, y equals the opposite of x. You can call it negative x if you want to. Any point. Give me 1 point. Any 1 point. I'll vote for negative 2.
Negative 8.
Negative 2, negative 8. Does that satisfy? Let's look at this. Y equals negative x, yes? If you plug in negative 2 for x, what would you get? Negative 2, which is positive 2. So if you plug in negative 2 for x, y has to be the opposite of that, which would be positive 2. Find me another point on the line. Actually, better yet, give me any x value that you can visibly see on the graph here. Give me any x value.
Negative 4.
Negative 1, I think I heard. Negative 1. Negative 1. What would the y value be? If x were equal to negative 1, the y value would be equal to positive 1. It would be right there. Whatever the x value is, the y is the opposite of it. You see how this is different? The last one was whatever the x value was, y was the same thing. This one is whatever the x value is, y is the opposite of it. So if x is negative 1, y is positive 1. If x is positive 1,
Negative 1.
y is negative 1. What do you notice about all three of those points? Do another one. If x is positive 2, what's y? Negative 2. What do you notice about these points? They're all on a line, aren't they? They're all on a line. What's the slope of that line, friends? What's the slope of that line? Negative 1 over 1, or negative 1. Yes. But once again, you guys nailed the solution right off the bat. Because where does that guy crisscross through the line y equals, 2x plus 1, right there at negative 2, positive 2, which means the solution to that equation is negative 2. You found the solution again, right off the bat. So the idea is, yeah, every single equation you solve, whether you solved them manually before or using the TI, all of them have a graph behind them. All of them have a graph behind them. We will not be graphing stuff by hand in here. I know you did enough of that. You did your time in that in your other algebra classes. We're going to be using the TI to graph stuff. But the idea of using the TI to graph stuff is still doing this. You're still creating those graphs and seeing where they hit. Where they hit tells you something special. Equilibrium points or solution points of the equation. So you have to know what you're pulling off of those. You have to know what you're pulling off of those. Now, in case, how many of you guys did, when Tammy was describing how she used her TI before to solve these things, how many of you guys remember doing that in 95 and graphing things, y1, y2, looking for them to intersect? Nice and high. How many of you remember doing that? So that's about 2/3. If you don't remember, we'll go back through it again. I've got some nice little booklets that will guide you through that too. But the idea is, there's a power in those methods. There's wicked power in those methods. They can take you past basic equations like this if you need to go past basic equations like this and start talking about exponential growth. Blake, that's why you kind of chuckled when I said, it's just exponential. Well, the cost of college increasing is exponential, 7% each year, percent. It's this exact argument, but the lines begin to curve. And all of a sudden people start going, oh my God, they're going to start curving? But does it matter? What are you looking for? You're looking for where the curves do what to each other? Intersect. When they intersect, it doesn't matter how nasty the original equation is. Where they intersect is the interesting point. And that's the point of these last 6. It wasn't to torture you by any stretch of the imagination. It wasn't to torture you. It wasn't the intent anyway. I apologize if it did. The point was to see that any equation can be solved with the proper graph, and part of the course is going to be designed as proper graphs, using technology most of the time. Yeah? Other questions you got right now? Any questions? Why the hell did I sign up for this course, perhaps? Maybe. Maybe. I'll give you some reasons as to why. I'll give you some reasons. Okay, make sure your names are on that before you leave, and we'll collect those. It'll be our first in-class quiz. Everybody happy with solutions?
Yeah.
Are we happy with our solutions? Let's make sure we got them. Let's go back to the beginning. 6x minus 2 equals 14. This is the very top of it. Well, we did these ones over here. 8 over 3. Anybody got 2.67? I like them both. Next one. 3. Quantity x minus 2 equals 12. Good. We like that one. X over 3 equals 7 tenths. 21 tenths. 2.1. Anybody put 2.1? It's fine too. Ding. That was good. X minus. Next one. Negative 39 tenths. Anybody go to negative 3.9?
Yeah.
Okay, good. There's me too. Me too. All right, now the graphical ones. Graphical. 0, negative 2, quantity x plus 1. That's the negative 1. I don't see any work on these quizzes. Am I going to take points off for that? Of course not, for God's sake. The point was using the graph, right? The point was using the graph. X plus 8 over 3 equals 0. X equals negative 8. X plus 8 over 3 equals 6. Good. 10, 10. Very good, very good, very good. This next one, x plus 8 over 3 equals negative 2. Quantity x plus 1. Negative 2. X equals x plus 8 over 3. X equals 4. And last but not least, bottom right corner, x equals negative 2. Please, bring.
Do you want our equation boot camp from last class too?
No, that was just practice. That was just, put that in your notes. If you guys are keeping notes, combine with that. Now I want you to sit back. Sit back. We got a little bit of time. I want to show you why the hell I just did this to you. With a context. Sit back, relax. Sit back and relax. I want to show you why I just did this to you.